All right, welcome back. So our next topic here in Unit 5 is the idea of points of inflection and concavity. So these are now dealing with second derivative locations and how it changes the shape of the graph. So concavity comes in four different ways you can look at it. Either it's concave up and decreasing, concave up and increasing, or concave down decreasing, concave down increasing. So you can kind of see like the concave up shape generally creates a positive looking parabola, whereas a concave down shape is generally a negative shaped parabola. Which kind of, when you think about it, makes sense. We talked about the second derivative test, being that when the second derivative was a positive value, it's a minimum. Notice right here in the concave up, which would be when the second derivative is positive, we have a min point. Whereas when the second derivative was negative, it created a maximum value. Well, that was what's going on right there. So you'll be asked different questions, different points, right, based off the original function, whether it's concave up or down. You're looking at the shape. If you're given graphs of the derivative of the second derivative, then we'll get into a little more detail what you look for both of those cases. So again, the concavity changes when the second derivative changes from positive to negative. So when the second derivative is positive, the graph of the function is concave up, whereas when the second derivative is negative, the graph of the function is concave down. And this change, where it goes from positive to negative or negative to positive, is called a point of inflection. This is where the second derivative is equal to zero. This is why it's so important to not think of the second derivative test for the idea of minimums and maximums as the second derivative equal to zero. The point of inflection is the second derivative equal to zero. It has nothing to do with the minimum and a maximum. There are some times when a point of inflection does correspond to a min or a max, but typically they are at different locations. Now again, this is also the idea where concavity is changing, so it does not, like with the min-max, the increase and decreasing analysis from your minimum maximums linear function first derivative test, we do need to also consider where the second derivative does not exist, because technically you could have a situation where there's a vertical asymptote, and then it's changing concavity on either side of it. So we do need to always consider where something does not exist. Now, first off, let's take a look at a couple graphs. So this is the graph of the derivative. And we want to know where in the derivative is there going to be a point of inflection. Now, we need to recognize that since the second derivative is where we're finding points of inflection, the second derivative is the derivative of the first derivative. And if we think back to the first derivative versus the original function, you'll find that in order for there to be a min or a max in the original function, you're looking for where's the first derivative equal to zero, which is it's going to be crossing the x-axis. So we know that -2, 0, and +2 could be minimums and maximums. But where are points of inflection? That's the actual min and max you see in the graph. So we see right here at -1, right here at +1, and then right here at +2. Those are going to be your three possible points of inflection, because they represent minimums and maximums in the graph of the derivative. Now, what's going on? Well, before this -1, this function is decreasing, and then it's increasing, and then it's decreasing, and then it's increasing. So wherever the function is increasing, it's concave up, which I'll just do is C with an up arrow. So that means it's going from -1 to 1, and then from 2 to 3, this thing would be concave up. Whereas it's concave down from -4 to -1, and then from 1 to 2. With, again, points of inflection where it does change, occurring at -1, occurring at +1, and occurring at +2. All right, so whenever you're given the graph of the first derivative, you're looking for minimums and maximums in that graph of the first derivative. That represents locations of points of inflection. All right. Whereas if you're given the graph of the second derivative, now we're looking for x-intercepts. And where are we crossing? So we have to show that it's crossing from above and below. So here at -3, here at +1, and here at +3, those would be our 3 points of inflection. Because the graph of the second derivative, when the second derivative is equal to 0 as a point of inflection, those are our 3 0 spots. Concave up, down, well, we are above before -3. We are below from -3 to 1, above from 1 to 3, and below again after 3. So concave up would be from -infinity to -3. We would use a -infinity here rather than just a number because it goes on forever there with the up arrow. And then again from 1 to 3. Whereas it is concave down from -3 until we get to 1, and then from 3 on to +infinity. With, again, our points of inflection occurring at -3, 1, and 3. So the location of a point of inflection concavity based on the graph is fully dependent upon the type of graph. We're going to talk more about analyzing graphs in 5.6, but the basic rundown for a point of inflection is if you're given the graph of the original function, look how the shape is changing, positive u's versus negative u's. If you're given the graph of the derivative, look where there are minimum and maximum points, whether it's a smooth curve or, again, we've got jagged spots. That's perfectly okay. It's still showing a change in sign, so even though technically it would not exist at those spots at -1 and 1 here because of the sharp turn, it would still be technically in point of inflection. And then the graph of the second derivative, you're looking for where are we crossing the x-axis. All right, so that's what it based off graphically. Algebraically, it's all about solving. We need to find the second derivative equation. So we go ahead and take our first derivative. We get a 1/2 cosine of x over 2. We take our second derivative. We get a -1/4 sine of x over 2. And we set that equal to 0. So ultimately, that coefficient in front didn't really matter in the slightest. It's all based on when is sine equal to 0, which based off the simple unit circle, sine is equal to 0 at 0 and pi. Now we should include some negative and positive coterminal angles because it says -pi to 3 pi. So going backwards, we'd have -pi, we'd have -2 pi. Forwards, we'd have positive 2 pi and positive 3 pi. So we multiply this whole thing by 2, because it's x over 2, we get -4 pi, -2 pi, 0, 2 pi, 4 pi, and 6 pi. Well, everything that's not in between -pi and 3 pi are crossed out, so our only points of inflection are at pi, 0, and 2 pi. But again, they are possible points of inflection. We still need to set up essentially the first derivative test, but for points of inflection. We're going to see, is there a change in sign here? So we go ahead and set up our table. So we have our interval. We would go from -pi to 0, 0 to 2 pi, and then 2 pi to 3 pi. We'll test -pi over 2, positive pi, and then 5 pi over 2. And we'll see whether we get a plus or a minus sign. So -pi over 2. So -pi over 2 divided by 2 would be -pi over 4. Sine of -pi over 4 is a -√2 over 2, so it's a negative value. We then go ahead, oops, sorry, I'm looking at the wrong one. I should be looking at -1/4, sorry. So yes, so it'll still be sine of pi x over 2 is still sine of pi -pi over 4, which is still negative, but it is multiplied by -1/4, so that really should be a positive value. Sorry, don't make my mistake. Make sure you're looking back at the second derivative, not the original function when you're doing this. So at pi, sine of pi over 2 is going to be 1 times the -4 is negative, so that's a negative value right there. And then 5 pi over 2 is 5 pi over 4, sine of which is a -√2 over 2 times the -1/4 is a positive value. So we can see we are changing. We do have positive concavity from -pi to 0 and 2 pi to 3 pi, and downward concavity from 0 to 2 pi. So these are true points of inflection. Because it's entirely possible, like with the critical point possibilities, you don't actually change sign at a location. So we have to always check that just to make sure. All right, let's do that for a simple polynomial equation. So again, we go ahead and take our first derivative. Just 8x cubed minus 8. We then take our second derivative, 24x squared. That's it. So that equal to 0, which means x squared is 0, so we get x equals 0 for our possible point of inflection. So we set up our table. We have our interval, we have our test value, and we have our sign. So we would go from -infinity to 0, and then 0 to infinity. So I'll test -1 and +1. And in both cases, because it's x squared, both times we get positives, so this is not a true point of inflection. There is no point of inflection for this problem. So again, because it's not changing its concave up the entire time, this is not going to be a true point of inflection. So always make sure you're testing it versus your secondary values. Essentially, you're doing the first derivative test, like I said earlier, for points of inflection instead. That's why it's commonly confused as what the second derivative test really is. This is not a second derivative test. This is just testing for points of inflection. They should come up with better names, to be perfectly honest. But Mathematicians are kind of lazy like that. For goodness sakes, we call normal lines normal instead of something special about it. So, right aside, moving on. So now we're talking about intervals of concavity. It's the exact same setup, but just a different way of phrasing the question. We still need to find the second derivative. We still need to set it equal to 0. We still need to solve and then do our little intervals to see where we're concave up and concave down. They're just phrasing it slightly differently. So first derivative is a quotient rule. So it's our low x minus 1 d high, which is 1, minus high x d low, which is 1, all over low low, which is x minus 1 squared. We get x minus 1 minus x over x minus 1 squared, which gets us negative 1 over x minus 1 squared. Which, to make my life easier to take a derivative, I'm going to rewrite it so it's a chain rule problem as negative 1 times x minus 1 to the negative second power. Always do that as making life a little bit easier when it comes to taking derivatives. If you have a quotient rule problem, but the numerator is just a numerical value rather than a variable, rewrite as a negative exponent and just do a basic chain rule. Because now we have negative 1 times negative 2 a positive 2, x minus 1 to the negative third power times 1, the derivative of the inside. So it's 2 over x minus 1 cubed. So there's no location where the numerator is equal to 0, so there's no actual physical point of inflection, but there could be a change based off the x minus 1 part. So there could be a change in concavity occurring at negative 1. So we do have to check out, positive 1. We have to check out what's happening there at positive 1. So we set up our table. So we're going to go from negative infinity to positive 1 and 1 to infinity. We'll test 0 and 2. So plugging into the second derivative, 0 minus 1 cubed is a negative 1. 2 over negative 1 is negative. So it's concave down in that interval. Substituting 2 in, 2 minus 1 is 1, 1 cubed is 1, 2 over 1 is 2, so it's a positive, so we're concave up. So there is a point of inflection at 1, and we are concave up from 1 to infinity, and concave down from negative infinity to 1. So again, asking literally the exact same question, just kind of phrasing it slightly differently. So that's a nice quotient rule situation right there. One more. Let's do a nice basic polynomial. Hopefully this one gives us actual points of inflection this time and not nothing. So we take our first derivative. We get 3x squared minus 30x. We take our second derivative. Get 6x minus 30. We set that equal to 0. And we get x equal 5 as a possible point of inflection. So we go ahead and set up our interval charts. We're going to go from negative infinity to positive 5, positive 5 to infinity. I'm going to test as 0, and I'm going to test as 6. I always like testing 0 wherever possible, so always use that if I can. Substituting 0 in, 6 times 0 minus 30 is negative, so we're concave down at first. Substituting 6 in, 6 times 6 is 36, minus 30 is a positive, so that's going to be a positive there. All right. So that means we are concave down from negative infinity to 5, and then concave up from 5 to infinity, with the point of inflection occurring at x equals 5. All right, so that's everything regarding points of inflection and concavity. Obviously, you can be dealing with different types of equations besides the ones that we discussed here in this video, but the rules still hold true and still apply exactly like we played it out here. Get to your second derivative. Sometimes more interesting questions will start you off at the first derivative, or they might even start you off at the second derivative. Either way, get to the second derivative no matter what you got to do. Set it equal to 0 and solve. More complicated questions, obviously, you can graph it and see where it crosses the x-axis. And if you are graphing, then the whole interval test chart is done for you, because if you have the graph of the second derivative where it's above the x-axis, it's going to be concave up, where it's below, it's concave down. So it just kind of depends on what you're allowed to use for that. All right, so our next video is going to be talking about analyzing and interpreting the graphs for all these kind of things. We're going to take a look at a bunch of AP-style questions for this. So I'll see everyone next time for that.